Hi, I'm Amilcar Soares, and I have prepared these three lectures about mining geostatistics. Well, you have learned the basic concepts of geostatistics in your introductory course. You learned how to calculate and modeling the spatial continuity characterization of a natural physical phenomena through very simple tools like variograms and spatial covariances. You learned the linear interpolation of sample values with different kriging methods also. Now, with these lectures, we intend to present some specific topics of application of those concepts of geostatistics to mining resources and reserves evaluation. Something that was coined by mining geostatistics by the pioneer works of André Journal and Michel David. Well, geostatistics are applied in several stages of mining practice, since, for example, like in this picture, from the early stages of exploration, where we just transform a set of geochemical sampling in 2D in a mapping, a continuous mapping of those chemical elements by doing a kriging in a regular grid of points until the estimation of resources by kriging the metal grades and classification. And this is precisely the area where the mining applications of geostatistics have some particularities. Let's start by the first point I would like to address in this lecture, which is the estimation of resources, the kriging of metal grades, and the classification of resources according the uncertainty attached to the estimates. But let me recall you a true story, which story of a company. This story happened at the late 19th of last century. A company named Brex. In fact, as a matter of fact, was a group of companies in Canada, and it was involved in a major gold mining scandal when it reported it was sitting on an enormous gold deposit at Indonesia. The company announced significant amounts of gold had been discovered, sending its stock price soaring. Brex Minerals, as you can imagine, collapsed in '97 after the gold samples were found to be fake. Incidentally, there is a fictional version of this story in a movie called Gold. Those pictures are from this movie, which I recommend to you for you have an idea how mineral resources were transacted in a very recent past. But the good part of this story was the creation of rules concerning resources and reserves declaration. For example, the most of the countries, mining countries, just define the regulations about those reported resources and reserves. I mean, in Australia, South Africa, Canada, etc. So in mining practice, the resources are classified according to geological knowledge and the amount of data used to estimate them. Just in one word, according the uncertainty of estimates. Let me tell you that in fact, mining industry was the first to use the concept of uncertainty to classify resources in order to report them to the stock markets and to transact them. And normally they are classified, classified in measured resources, indicated resources, inferred resources, according to the decreasing level of knowledge and confidence. So the first step consists on the estimation of resources. Basically, we transform the discrete sample of data into a continuous model by doing, for example, kriging of grades. Afterwards, we proceed to classification of resources. which basically consists, for example, of using structural distances of the samples to the estimated point or block. Structural distances, it is not Euclidean distance, it's the use of the equivalent value of variogram or spatial covariance. For example, take the example of this picture. We can define three main distance limits. For example, d1. D1 corresponds, for example, to 2/3 of the seal. D2 coincides with the range of the variogram, and D3 greater than the range of the variogram. So basically, on those distances, one Kriging point or block located in x0, for example, is classified as measured if it was used at least n1 samples with a distance to x0 less than d1, the first distance, or indicated if it was used at least n2 samples with a distance to x0 less than d2, and inferred the whole blocks or points that it was used at least n3 samples with the distance greater than d2. Those values n1, n2, n3 depends on each case, on the heterogeneity of the ore body that you are dealing with, and so on. So we sometimes we can use also a second criterion that is related with this clustering of samples. For example, one Kriging point or block x0 is classified as measured or indicated if it was used at least one samples from the same cluster borehole. Note that a borehole samples coming from a borehole are considered clustered samples. So, but the important thing is with these two criteria, the same used in the Kriging variance, incidentally, structural distances and the clustering, one wish to quantify the uncertainty of classification of resources. So, second, this is another point. This is the second issue I wish to talk about in this lecture, which is the use of different types of sample data to Kriging your resources. Basically, one should use data with same support, borehole samples. Okay, but take this very naive example. If you average 1 meter samples in 4 meter support samples, we obtain two sets with the same mean, same average. So different support data may have different spatial variability. In this case, should not be integrated in the same conditioning set to estimate resources and reserves. You should avoid to use them together to create one point or block. Okay. Let me give you one very common example in a mining practice: the use of face samples and borehole samples. During a mine operation, usually face samples are taken from the available fronts. Okay, so very often they are used just for geological control rather than for kriging of resources. But now let's see if you use both samples to estimate the resources. You estimate and updating resources, kriging the main metals using both borehole data and face sample data. What happens is, suppose you have borehole data and much more dense set of face samples taken during the production. If the face samples are considered reliable, and some comparison tests with the neighborhood borehole data can be done to confirm that. So you check with borehole data and at the neighborhood, and you can confirm if they are reliable or not. In principle, we must not reject the face sample data. Follow a basic principle. Even uncertain data is better than no data. So let's see. There's the use of different types of sample data to Krig or research. Suppose we have Z1 of X, the copper grades or any other metal from borehole samples, and suppose you have Z2, the same equivalent grades from face sample data. Now, this is a basic rule. If Z1 and Z2 have the same statistics and same variograms, they can be used together in a kriging and classification procedure as just one variable, Z of X. Okay. Otherwise, if they have not the same spatial continuity, same variograms, spatial variability, and so on, they can be used in a joint simulation procedure that we have learned in the introductory course, like kriging. Now, let's see the third point I would like to address in this lecture, which is kriging with geological control. Here, this is a concept which is called ore type. Ore type is a homogeneous geological mineralization with identical chemical contents, okay, but with identical mineralogical characteristics. I mean, the behavior at the ore dressing plant. For example, suppose, for example, copriferous ore type or zinciferous ore type can be identical sulfide mineralization, but with high copper grades or high zinc grades, respectively, with different ore dressing plant treatment. They are considered here different ore types. They are different ore types because they require different mineralogical treatment. So all types resources must be estimated separately, as they are mined and treated separately. One intends to preserve the grades distribution inside each ore type. First, at the very beginning, the ore types are identified in the borehole samples. Suppose in this pretty naive example of the picture, we have 3 ore types characterized by different boreholes, in the different boreholes. Basically, the first thing that we have to do to be sure is the ore type spatial domains must be defined previous to the estimation of grades inside them, which is called kriging with geological controls, when we have the domains conditioning the estimation or the kriging. Okay, so to characterize the ore type boundaries, there's several procedures. The more typical or more common procedure is to, after classify the samples in ore types, the most common is expert or expert classification or geological interpretation, or basic on the geological characteristics of the samples, or mineralogical, or if there is or not contaminants, and so on. Another classification, for example, can be a numerical classification. We can define, for example, a ore type based on if the grade is higher than a cutoff or lower than a cutoff. Okay, so in the second step, we can, based on the sample values or qualitative values of ore types, we do some kind of interpolation, normally deterministic interpolation of 3D ore type boundaries. We can use expert geological interpolation, polynomial interpolation, splines, radial basis function, and so on. Okay, sometimes sometimes you can use geostatistical interpolation methods of ore type boundaries, but like, for example, using indicated kriging But just in those cases with homogeneous mineralizations that do not need expert or the geological intervention, okay? So, kriging with geological control can be summarized in those steps. We define first the spatial continuity analysis, variegated models of main grades inside each ore type. And for each ore type, we have a model of variegram. For example, the gamma X being X, the ore type A, B, or C. Those are the models. And afterward, the kriging is of any grade inside of ore type is a linear combination of samples of that ore type, A, B, or C. Okay. This is illustrated in this case. To estimate any point x0 belong to ore type A, only samples of A and variegated models of A must be used. Okay. This is what we call kriging with geological control. Another point, let me call your attention for another important issue that comes with kriging with geological control. Suppose that this layer of a given ore type with a more complex morphology, this folding at the end here. Okay, this is the global model. And then this is the global model of covariance that you use to estimate the grades. But can you see locally there's a contradiction between the global structure model and the local orientation of ore type layer here at the end. Okay, so what we do in those cases is what kriging with geological control by applying what we call local varying anisotropy models, which is very simple. Instead of using the global model of covariance in top figure, where it will produce some artifacts, horizontal artifacts where the layer is folding, we use local anisotropy models like in this one. Okay, that's what we call local varying anisotropy. The fourth point of this lecture that I would like to approach is about kriging search neighborhood strategy. This is where it comes from. In all rigor, in order to the unbiased criteria condition of kriging to be accomplished, all sample values must be taken into account in order to estimate any point x0. Okay, but given the high number of samples, such condition is most of the time impracticable. So to estimate one point or block, one needs to select a representative set of the neighborhood samples. Well, the first note I would like to emphasize is about the dimension of the search neighborhood, which means that the larger is the local search neighborhood, the more is the smoothing effect. For example, take those two situations, A and B, the histogram of estimated grades in those two situations, estimated grades Z of X of Aster, this histogram of estimated grades reflect the smoothing effect here. The smoothing effect of which means that the extreme values are less represented in situation B. So another issue is what we call screening effect. Some models, for example, some variegram models, sorry. For example, spherical and exponential models with no negative effect tend to screen the influence of samples by giving the most of the weight to the closest samples to the point to be estimated and very low weights to so far away samples, okay? Well, the screening effect can lead to negative weights of kriging, and consequently estimated negative grades. And the reason is simple. The unbiased condition of kriging assures that the sum of the weights should be 1. but the weights cannot be positive, can be greater than 1 and lower than 0. Okay, that's the reason of those effects. Now, this in practical terms, the screening effect happens when the search range of samples, of the samples to Kriging one given point, it overpasses the range of the value ground. So this effect can be limited. I mean, the screening effect can be limited by reducing the range of such neighborhood. Okay. So the last point is related with the clustered samples like borehole data. So any samples coming from a borehole is always considered a clustered sample. So any point close to a borehole can be estimated just with samples from that borehole. So, and it can be a biased estimated. If we define, for example, just estimate with 8 to 16 samples, and those samples come from the same borehole, the resulting estimated can be biased. Okay, so in short, in presence of clustered data, the most common search strategy consists in limiting the number of samples by quadrant in a 2D examples or estimations, or octants in a 3D cases. Okay. So the last point that I would like to address in this lecture is called block kriging. Let me tell you one thing, that resources most of the times are estimated in point support. Okay, so we estimated points and we have an idea about the spatial dispersion of our resources. Okay, so but the point is, reserves normally are defined in a block support, which is with normally coincides with the stopes to be mined, to go to send to production, or send to this way or another way, and so on. So the ore type classification, mine planning decision, etc., are taken at block support rather than point support. So, block support estimated grades. Suppose that, let's call ZV is the average grade Z at the block support V, not the point, located at X. And Z of X is the grade at the point support located at X inside V. Okay, so the real grade value, the real grade value at support V is the volume integral of point support grade Z inside V. This one is integral. Okay. If the volume support, this is represented is an illustration into the illustration, but if the volume V stope is discretized in a set of points, such a way the real grade values at support V ZV is equal to, is the sum, is an average of all point grades inside V. Hence, obviously, the estimated grade ZV is equal to the average of point estimated grades. Okay, so this is the simplest way to get a value, average grade, a Kriged average grade of a block. But we can also Kriging directly the grade content of a regular block support. Okay. In some mining operations, for example, open pit mines, the unitary stopes are regular blocks of the same dimension. In those cases, it's very practical to estimate the values of Z can be estimated directly by ordinary block kriging as a linear combination of the surrounding samples. Let me see. So, for example, the ZV, the estimate of a block is a linear combination of samples, classical, okay, that you have seen in a point support estimate. So ordinary kriging of the ZV of this value is a linear combination of n neighborhood samples Z x of alpha. Alpha is the surrounding samples, which takes into account the two basic criteria regarding the estimation errors, the classical ones. Oh, the unbiased condition, which entails the sum of the weights must be 1 and the minimum estimation variance. Those two conditions you know it very well from the introductory course that you have taken. It's exactly the same, except two terms related now with the block value ZV, not the point value. And those two terms are this one, which is the average covariance between the block, the points inside each block, okay, and the average covariance, which is called point to block covariance, which is the average covariance between any sample and all the points inside the block. So in short, we have the point block covariance, which is the mean of covariance between the sample X alpha and the points within V, this one, and the block covariance is the mean covariance between the points within V, okay, yeah, this expression here. So the ordinary kriging system is a classical that gives the solution of the n weights attached to each sample to estimate the block. So that's all I would like to talk about mining geostatistics in this lecture. In the next lecture, we'll see one also important point, which is related with support effect and recovery functions. Okay, thank you.